To carve a block of granite, you must apply immense physical force to fracture crystalline rock at precise geometric angles. The knowledge required to do this successfully, generation after generation, is a refined form of engineering. In the study of traditional art, we define this as traditional knowledge, an accumulated record of empirical observation, strict material testing, and environmental interaction. We tend to romanticize historical artworks as pure expressions of culture, myth, or spirituality, but the physical creation of these objects is rooted in a demanding, unforgiving material reality. Before a sculptor or painter can express a complex theological concept, they must first master the chemical and structural constraints of the raw materials pulled from the earth. Those raw materials are often deeply hazardous. The vibrant colors defining classical paintings are derived from toxic heavy metals and corrosive mineral compounds. This safety document outlines severe hazards of pigments like cerussite and cinnabar. Cinnabar and vermilion are highly toxic, absorbed through inhalation or ingestion. Prolonged exposure to these dry pigments results in severe physiological damage, including tissue lesions, heavy kidney damage, and central nervous system impairment. To work with these materials safely, traditional artists had to operate with laboratory-level caution. Today's modern guidelines mirror these ancient necessities, demanding NIOSH-approved respirators, strict isolated ventilation, and strict wet mopping procedures specifically to keep the lethal microscopic dust out of the air. Because of these physical and chemical demands, we must analyze traditional art through its mechanics of construction. To understand how these materials are manipulated, we categorize the techniques into three structural domains: three-dimensional mass, two-dimensional transfer, and two-dimensional surface integration. The first structural domain governs the manipulation of three-dimensional form. Sculpture relies on the precise tension between two elements. The first is mass, the solid physical bulk of the material itself. The second is space, encompassing both the air wrapping around the exterior edges and the negative hollows enclosed within the form. Creating mass happens through subtractive or additive processes. Carving is strictly subtractive. The artist removes material from the original block until the final form remains. Modeling is additive, allowing the artist to continuously build upon and reshape a flexible material like clay. This additive flexibility is pushed even further by casting techniques, like the ancient cire perdu or lost wax process. By creating a hollow mold from a sculpted original, artists can cast molten bronze into top-heavy, highly complex structures that would instantly collapse under their own weight if carved from stone. Regardless of the method, the manipulation of mass and space is governed by 5 strict principles: orientation, proportion, scale, articulation, and balance. Orientation dictates how a figure occupies its environment. Sculptors calculate this using cardinal planes, engineering stances like the contrapposto or chiastic pose, where the weight of the massive stone rests dynamically on a single leg, forcing the body to twist gracefully across different axes. The final visual appearance of a statue is the direct result of the specific mathematical and compositional rules the sculptor uses to solve the physical constraints of the material. We can trace exactly how variations in these engineering principles create distinct cultural styles by observing the historical progression of the classical Indian Buddha. The Gandhara style applies distinct Greco-Roman proportions. The facial features are large, outlines sharp, and mass is defined by thick strokes simulating folded drapery. Contrast this with the Sarnath Buddha style. The body is slender. Rigid lines are replaced by subtle drapery, merging seamlessly into the soft physical body. By altering their approach to proportion, scale, and surface articulation, these different guilds of artisans literally engineered solid rock to manifest specific, shifting theological ideals over centuries. The second structural domain shifts away from permanent mass to focus on the mechanical transfer of two-dimensional imagery. Printmaking manipulates a matrice's topography. In relief, negative space is carved away. Ink is rolled over elevated plateaus to transfer the design. Intaglio is the opposite. Grooves are incised, filled with ink, and retrieved by forcing damp paper into the recesses. The method of creating those intaglio grooves determines the texture of the final print. Etching uses controlled acid baths. Engraving relies on a sharp burin, Drypoint scratches to leave a burr, and Mezzotint uses a toothed rocker. Through this strict mechanical engineering, printmaking allowed visual information to transition from a single, isolated physical object into a reproducible dataset. The final structural domain concerns the chemical integration of color onto two-dimensional surfaces. At a basic physical level, paint is simply a dry pigment powder suspended in a binding medium, like oil or water. To stack layers safely, artists use the fat over lean principle. A fast-drying lean layer placed over a slow-drying fat layer will severely crack. Each successive layer must contain a higher ratio of oil to remain flexible. Once chemical stability is achieved, artists manipulate the physical texture. They can use impasto, applying highly concentrated thick layers to build physical ridges that catch ambient light. Or they can use glazing, applying incredibly thin, translucent layers of medium that act like colored cellophane over underlying shapes. But the ultimate form of surface integration is the fresco. The pigment is not merely topically applied. In a true wet fresco, water-based pigment is applied directly onto a layer of freshly laid lime plaster. As the plaster sets, a chemical reaction occurs. The pigment physically bonds with the matrix, becoming a permanent, structural component of the wall itself. This specific chemical transition allows two-dimensional imagery to scale up and become permanent architectural structure. We see the durability of this architectural integration across the monumental rock-cut sites of India. Large-scale fresco painting maps an evolutionary line through classical history. It begins with the profound maturity of the Ajanta style in the late 5th century CE. These early caves are defined by complex, voluminous compositions, sinuous lines, and distinct features like heavy-lidded, half-closed eyes. That tradition extended south under the Chalukya dynasty. In the 6th century, artists excavated the Badami Caves, creating the earliest surviving Brahmanical paintings in the famed Vishnu cave. By the 11th century, the Chola kings reached the height of their power, deploying this mural technology inside the towering Brihadisvara temple at Thanjavur. As the timeline moves into the later Vijayanagara and Nayaka periods, the visual data shifts. The spatial modeling flattens out. Figures are presented strictly in profile against stark backgrounds, and the sprawling scenes are organized into strict rectilinear compartments. This continuous historical lineage acts as an exposed geological record. We see shifting regional priorities mapped perfectly alongside advancing chemical and architectural capabilities. 3 distinct structural modules: the manipulation of mass, the mechanics of transfer, and the chemistry of the surface. The production of traditional art required absolute precision within these domains. An artist had to calculate the exact load-bearing capacity of a massive bronze cast, calibrate the precise acidity of a metal etching bath, and mix the perfect lime ratio for a Chola temple fresco. A failure in the math meant the physical destruction of the work. Look at the sheer scale of the Kailasa temple at Ellora, an entire architectural complex excavated downwards out of a single piece of volcanic rock. To truly admire traditional art is to recognize the rigorous, empirical engineering required to reshape the physical